Okay, ladies and gentlemen, listen up please. Welcome back to Vector Calculus. In today's lecture, we're going to continue with line integrals. And if you remember, we've motivated line integrals. We've defined what they are and computed some of them. We've looked at 3 different kinds of applications. And today, we're going to talk about the so-called fundamental theorem of line integrals. Okay? Now, remember, we're talking about vector calculus here. The calculus that you learn at school involves a fundamental theorem of calculus. And then when you get to university, you realise, well, there's really 2 fundamental theorems of calculus for functions of one variable. Now, an interesting question is, well, we've looked at these line integrals. Is there a fundamental theorem for these line integrals? So that's the question that we're going to be answering today. And the answer is yes, but sometimes, only sometimes. Right? Now, when we looked at path integrals, I gave a challenge to the group saying, can you formulate a fundamental theorem of path integrals? Okay, I might have discussed it in the tutorial, one of the tutorials. But the problem there, as you pointed out, it's not very useful. Okay? It's not very useful. So what we're going to do today is, yes, we're going to develop a fundamental theorem for line integrals, and it's going to be very useful. Very useful. Okay. So, some vector fields possess a property known as path independence, where the line integral of a vector field between starting at point P and ending at point Q, it only depends on the endpoints. Okay? Now, the important thing to note here is that in this case, it does not depend on the path travelled between P and Q. So, think of 2 points, say, in the plane, and any 2 paths, starting at point P and ending at point Q. The line integral of a vector function would be the same, no matter which path you travel along. Now, a vector field with this path independence property is called a conservative vector field. So, in this diagram here, you can see, right, here, we're starting at this point P, we're ending at this point Q. Here's one path parameterized by a vector function C1. Here's another path parameterized by a second vector function C2. And the line integrals over both these curves will be equal when f is conservative. All right? So when f is path independence. So, essentially, what we're going to do today is develop a theorem that only involves the endpoints of the curve and not the path between them. That's very powerful. That's a very powerful idea. Now, to do that, we will employ the idea of a so-called gradient vector field. Okay? And we call a vector field a gradient field or a gradient vector field if there exists a scalar field phi such that the gradient of phi equals the vector field f. So usually f is a given vector field, and it's up to you to produce some scalar field phi such that grad phi equals f. That's the basic idea. And this phi is called a potential function, or just a potential for short. Okay, so let's investigate this a little bit further. So let's define, what am I going to do, xi plus, x squared I plus yj. So is this vector field a gradient field? Okay, so what we would like to do here is to produce some scalar field phi such that grad phi equals the given vector field. Okay? So we try to construct a function, phi, such that grad phi equals our vector field. Okay? So what we want to do here is solve d phi dx equals x squared, d phi dy equals y. Right? Okay, so we've got two differential equations there, basically, and they can both be integrated quite easily. So integration yields the following. So if I integrate d phi dx equals x squared with respect to x, I'm going to get something like phi equals a third x cubed plus function of y. Okay, remember we're talking about partial derivatives here, so we don't have really constants of integration. We have, I guess, functions of integration. The integration on d phi dy equals y gives a half y squared plus v of x. So what we would like to do now, if possible, is to choose functions u and v such that these two equations are one and the same. Okay? So can anyone think of a choice for u? Yep. Seems pretty easy. Can anyone think of a different choice? Yes. You can have a constant in there if you really want to. And v of x would be something like a third x cubed. Okay? Through those choices, the two equations are one and the same, right? Thus, we have phi to be 1/2, let's do the x first, 1/3 x cubed plus 1/2 y squared. If you really want to, you can put a constant in there. So the answer to our original question, is this vector field a gradient field? Well, the answer is yes. And here, we've actually produced a scalar field, and you can check that grad phi equals the vector field f. You can check that. Okay, so that's a pretty easy example. Let's do something a little bit more engaging. Actually, I'll get to that in a minute. Okay, a similar type of question here. Let's consider the following vector field. Okay. The question is this a gradient field? Is this a gradient field? Well, is it? Yes? No? Well, let's find out. So we try to construct a scalar field phi such that grad phi equals f. Okay, so just like the previous example, we want to solve some partial differential equations. But here we're going to have three partial differential equations to solve. So we want to solve d phi dx equals y. We want to solve d phi dy equals z. And we want to solve d phi dz equals x. Now those three equations can be integrated, but the rub is when you try to choose the functions of integration. Okay, so integration will yield the following. Okay, so I've integrated this one. Integration of the second one will yield this. And integration of the third one here okay, so u, v and w are functions that we are hoping that we can choose to make the three equations one and the same. Now the question is, can we make those choices? No, we cannot. No matter how hard we try, we cannot choose functions u, v and w to make those three equations one and the same. We cannot do it. It's impossible. Right? So we recognise that no choice of u, v, w will make our equations one and the same. So we're a bit disappointed about that. So to get back to the original part of the question, is f a gradient vector field? The answer is no. Okay? So thus, f is not a gradient field. Now it seems like a lot of work to go through and try to solve three partial differential equations. Okay? What we're after here is sufficient and possibly necessary conditions to understand when we have a gradient field and when we don't.
Yeah, should we check whether the divergence is zero?
Divergence?
The divergence.
You sure?
And article.
Curl, that's it, yes. That, you're about two slides ahead of me. Okay? So just bear with me. And the answer to your question is yes, the curl does come into it. Okay? All right, now this next slide is the focus of the lecture today. This is the most important thing you're going to see in the lecture. All right, so take note. The fundamental theorem of line integrals. Here it is called the fundamental theorem of gradient fields or gradient vector fields. And it's a theorem that has sufficient conditions under which the line integral is very, very easily calculated. And in particular, the line integral will not depend on the path. It only depends on the initial point and the terminal point. All right, so let's read it. If there is a scalar field phi such that grad phi equals f on some domain, then for every oriented curve, curly C, in the domain, with initial point P and terminal point Q, we have the following relationship for the line integral of f over C. So try to relate that to what you already know. This is a generalization of the fundamental theorem of calculus that you learnt either at school or at first year university. Okay? An integral depends on the value of the antiderivative of f, in a sense, at the endpoints only. Okay? That's a massive theorem. That's huge. Okay? It also has some big implications, not only for computing line integrals, but for calculating work done on moving particles around. Okay? So there's a second, I guess, a special case of this fundamental theorem. If C is a closed curve, then the line integral of f around C is 0. Right? Why? Because the start point, or the end point and the start point are just the same. So the value of phi at those points is the same. Right? All right, so the proof is relatively easy. It's a big theorem, but the proof is relatively easy. So we apply the chain rule for paths to look at this derivative. Okay? Essentially what we want to do is turn our integrand into the derivative of something. All right, so suppose we parameterize our curve curly C by a vector function, and it's regular and smooth enough. Now C of A is going to represent the point P, the initial point. C of B is going to represent the terminal point. Okay? So the vector function C of T parameterizes the curve C for T between A and B. All right. So let's calculate this derivative here. Now the chain rule for paths tells us that it's just grad phi along the parameterization dotted with C dash of T. Okay, so how does that help us then? Well, so here we've used the chain rule for paths. Okay, so now we're going to use the assumption that f is a gradient field, right? So our line integral can be written in the following manner. Okay. So what we do now is incorporate the parameterization, and you'll see that we end up with a beautiful cancellation. All right, so we're at this stage. We know that this is just here, so we can replace this with the derivative here. All right, so if you look closely now, we have the derivative. Our integrand is just the derivative of something. So we can write our expression in the following way. Okay. Now, C of B is just the point Q. C of A is just the point P. So we obtain our desired expression. Okay? Nice, simple proof, but a truly enormous result. Okay. Right, so let's look at an application of this fundamental theorem. How does it actually help us to solve problems? What are the physical implications? Okay, so this is a good question. Determine the work done by this vector field along any smooth curved curly C from this point to this point. Okay, now note that I'm kind of giving the game away a little bit there by saying conservative here, but in practice, what we'd like to do here is set up a potential function, right? So an important thing to note here that C is not prescribed. Okay, it could be any path between P and Q. Okay, so our job here is to choose, if we can, a potential function such that yes, well, if you can break it down into so for example, there's a corner, right, in the curve, say. Okay, you can break it down into two sufficiently smooth subcurves, right? And then integrate over those subcurves. What's that? Yeah, I mean, I've used the word smooth there just to minimise space, right? I'm not going to put down every technical detail in this. I'm a very simple man. You know that, Godfrey, right? Okay. All right. So we try to find a phi such that grad phi equals f. Now I know it's all on the tip of your tongues. What's phi going to be? Huh? XYZ, yes. Where did that come from? Well, you can probably guess in these situations, right? Okay. So we can choose phi to be xyz plus or minus a constant. Now, I'm not going to bore you with the details, but to produce that, you would just go through the motion, set up 3 partial differential equations, solve them, and then choose your functions of integration in an appropriate manner. All right? So you can see that. Okay? Now, what does this mean for the computation? Well, it means that the computation for our line integral depends on the endpoints only. So we apply our fundamental theorem to obtain the following. The line integral depends on the initial point and the terminal point only. So, at 1, 1, 1, phi is going to be 1 times 1 times 1, and at the origin, phi is 0. So, okay. All right, so we've solved our problem. We're delighted. We're delighted. Notice that the solution is greatly simplified from our previous examples. Okay, so what we'd like to do now is to develop some sufficient conditions, even better, necessary conditions, under which we know we are dealing with a gradient field. Okay? Now this theorem is in your notes, but I thought that the font was a bit small, so I've beefed it up for the video. All right? So suppose that our vector field F has components with continuous second-order mixed partials. And this is the important thing. If F is a gradient field, then the curl is the 0 vector. Okay? So in other words, gradient fields are irrotational. We talked about that in a previous lecture when I introduced the curl. Gradient fields are irrotational. Okay. So if there is a scalar field such that grad phi equals F, then the curl is 0. In other words, these equations hold. But is that a useful theorem? Why not? That's right. This theorem, it's reasonably interesting, but it can really only tell you when you don't have a gradient field. So it's only useful for ruling out fields such that they're not gradient fields. What we would like to do, as you say, is have some sufficient conditions that imply you do have a gradient field, right? But still, this is reasonable. This is reasonable. So, oh, by the way, how would you prove this? Well, it's very easy. Okay, if F is a gradient vector field, we can replace it with grad phi. And then if you work this out, assuming that, for example, Clairaut's theorem holds, then all the components will be 0. Okay, if I have time, I'll come back to that, but I'm not going to do it right at the minute. Okay, it was actually one of the identities I showed you in the previous lecture on curl. I don't think I proved it there, but the important thing here is, for that proof, you need continuous second-order mixed partials. Okay, but I'll come back to that if I have time. All right. Show that the following vector field is not a gradient field. All right. So for this one, you can show that the curl is non-zero. Now, really, all you need to do there is show that, where are you? Show that at least one of these equations doesn't hold somewhere. Okay? That's good enough. All right? So on this one, if this is, say, F1, F2, F3, then you can show that df3 dx is not equal to df1 dz at least one point, right? Okay, so what does that mean for the context of calculating a line integral? Well, I'm glad you asked. It means that you cannot use the fundamental theorem, right? Okay? So F is not a gradient field. Okay, so we're going to have to do it the traditional way. Okay, so let's see if we can produce a slightly more useful theorem. And this is what you were talking about before, right? And this isn't in your notes. This is just for you guys for coming to the lecture today, right? Suppose you have a vector field, F, and we have what's known as a simply connected region, right? So a simply connected region basically means there's no holes in the region. So think about working in the plane in R squared, right? A simply connected region would be a disk, all right, or an ellipse that's filled in, or a square, a rectangle that's filled in. Okay, what's something that's not simply connected? Donut. Okay, right. So suppose we have this vector f. Let f have components that are continuously differentiable, C1. If the curl is 0, in other words, if the vector field is irrotational, then f is a gradient field. That's a much more usable theorem than the previous one. Okay? That's a much more usable theorem than the previous one, because given a vector field, we immediately can apply this and know that it will in fact be a gradient field. All right. Okay, let f be defined in the plane as xi. Show that if c is any path from this point to this point, then the line integral is given by c squared minus a squared all on 2. Okay, so here f1 equals x, f2 equals 0. Suppose, let's go back to our theorem. Now, because the given f is in the plane, this is the only thing we really have to check. All right? Okay, so df1 dy is going to be 0, and that's also equal to df2 dx. Now, I know you can work this out in your head. Yes, I can compute the potential for this very easily, but there will be cases when it's not so easy. Okay, so it's always good to do a little test to see if what you're looking for actually exists. Okay? All right. So we know that we must have a gradient field on our hands. Great. So we want to solve these two differential equations. They're easily solvable. Say a half x squared. Okay, so now we can go back to the identity that we want, apply our fundamental theorem, okay, so it's going to be phi of c comma d minus phi of a comma b. So that is just a half c squared minus a half a squared, and we get the identity that we're looking for. Okay, so in the next slide, I have actually done a field plot of this is the vector field. So if my start point is, say, here, and my end point is here, then it doesn't matter which path we take, between the 2 points, our answer is always going to be the same. Okay, so let's think about what implications that has on, say, in a physical setting. Now, the gravitational vector field, that's a gradient field, right? So what does that mean? It means that if a particle is moving and gravity is acting on that particle, the work done by gravity depends on the initial point and the end point only. It doesn't depend on the path that the particle travels. Okay? If I remember correctly, electrical fields are also gradient fields, right? Okay, well, next week we're going to do Green's theorem. Massive theorem. You thought the fundamental theorem of line integrals was big. Wait till you see Green's theorem. Okay? So have a great weekend. I'll see you all next week.